Bismillahirrahmanirrahim. Uh, After such a long debate about how should we continue during this break, rather to go on the online lecturing or pre-recorded one, so I decided to go for the pre-recorded lectures rather than the online because there are a number of the students who are facing problems in the internet connections and sound quality and video qualities. So I preferred that I should rather than to wait for the online lecturing, we should go for the pre-recorded one. So I'll keep on doing these pre-recorded lectures for all you guys, and then we'll keep on uploading on the either on the YouTube or will be given to the link will be given to you so that you can access it and download it as per your convenience, and then we can go ahead accordingly. And the methodology what coming into my mind is right now that I'll keep on uploading the pre-recorded lectures for you guys, and then we can connect on either on WhatsApp or on the Google Classroom, where you can pose the questions. We can have a discussion. That discussion may join by different group members, or we can use this Zoom platform only for the discussion purposes, so that the technical issues you people are facing can be deal with accordingly. और अगर आप लोगों को कोई confusion है तो we can discuss accordingly. So this will be our methodology: pre-recorded lectures, and then we can have a discussion sessions as per the convenience of the class. So where we were in chapter 3. Almost theory was done. Today what I'll do, because it's a long time now, what I'll do that I'll revise the chapter 3 quickly, and then we will solve some numerical problems from the book, and then we will discuss some examples, uh, and then we will conclude this chapter. Probably today's lecture will comprehend all of the part of the chapter 3 that we need to cover for this course, except the gear problems. So I'll discuss the gear problem accordingly in my next lecture. That will be a not very big lecture. That will be a small lecture discussing primarily about the gears, and one or two the formulas will be there, and then we will deal with the one problem probably, and then we will end up this chapter. So let's start from the revision. These are basically the notes which I prepared for the class. So I'll quickly go through this so that you can have an idea what we have been doing in previous classes. So we started chapter 3. Chapter 3 is about the torsion. Chapter 1 and chapter 2 deal with the normal stresses, as everybody knows that if we have a bar of length L, and then a torque is applied on it, so what will happen? There will be no change in the length, but there will be some twist, angular change will be there. We keep on discussing all the equivalent analogies, that in chapter 2 we have the normal load P, and then we have the normal stress sigma. Epsilon is the strain, and then delta was the deformation, or the change in the physical parameter of the system or the device or the component, and nu was the Poisson ratios. So in this particular chapter we will be dealing with the torque now. Torque, and then resultingly we have the shear stress, torsion, we say normally to torsion, and then we have the angle of twist, yeah, angular twist basically because of this torque, and then we have the change in the angle, that is the phi. So these are the equivalent analogies. P is equivalent to T in this chapter, sigma is equal to tau, epsilon equals to gamma, delta deformation was equal to the change in this particular change in angle because of this twist. So if you remember, we deal with the when we have a torque applied on a particular beam, so twist is there, so that twist deals with the torsion. So if we have a torque T of 10 kips per foot, so if we cut this section over here, so we will have some internal forces. Just like we had the P normal force, P that was a normal force we were applying in the on the system or on the beam, and resultingly sigma was generated. Sigma was the internal behavior of the system, resistance to that particular load that is being applied externally. So in this particular case, since we are twisting that particular one, so so internal stresses will be there, and these external stresses will be called shear or the torsion by the end of day. So again, formulas are same. We had the tau was p over sigma was p over a. So here it will be again load over the per unit area in this particular shear case tau. Second part, a static part was that if we have two torques there, 10 and 20, both are basically anti-clockwise, and if we take the section over here, BC section, so what will be there? So we know it should be 10. And if we take the section over here, at this particular one, uh, I don't know why my pen is not working over here. So if we take the section over here, so it will be 10, and if we take the section over here, so it will be 40, because both are in the clockwise directions. And if this is in the counterclockwise direction, it will be in the clockwise direction like this one, 30, so it will be obviously 20 over here, and it will be 10 over here. Third part was the static, was that if we have a 3-axis stress, x-axis, this is x-axis, this is y-axis, and this is our z-axis. This is our z-axis. So if you are applying torque in this direction, that is a special type of the moment that is called torque. It can be in this direction as well. So it will be Ty then, if we are applying torque in this direction on a particular beam. And rest of the two will be, if this is x, if we are applying torque in this direction, so rest of the two, that is y and x, z, will be causing the moment, causing the bending. So that is called moment. So torque is basically special type of the moment which is applied along the axis of the beam, and that cause twisting. The rest of the two will be cause the bending. So that is why they are called moments. So no difference between torque and the moment, except what is the output. If the twist is there, so that moment is called torque. If bending is being caused, so that is the pure moment. So in one direction, when you deal with the 3-axial stresses, three axial moments, so one will be called torque, and rest two will be called moment, that will be causing the bending as well as the torque, that will be the torsion there. So when we go on chapter page 2, so we have already done that it is the center over here, and then if we apply, this is the center of this shaft, and two equal and opposite forces are being applied, having the area of dA and dF. So there will be an opposite area equivalent to dA. Obviously that will be having opposite force on that one. So these two equal and opposite force which are not sharing their line of action, they are called couple. And we know whenever there is couple, there is some twist. So twist will be there, and by doing all this stuff, we end up with this one, which is the first expression was this one, that was tau delta A into rho, that was equal to torque. So then we have the angle of twist. When we apply a twist on that, so that is the gamma now. In that particular case, if we keep on doing all these derivations, so gamma will be 5 rho over L. Rho is the distance from the center to that particular dA, and it is maximum distance, that is the radius of that, is basically the C over here. Uh, so uh, so when rho will be maximum, that will be equivalent to 0. So it will be C over L, and the gamma will be maximum. So maximum shear strain will be there when gamma becomes equal to C. And when gamma is equal to 0, so no distance, so everything will be equal to 0. No strain will be there on that particular one. And then if we keep on going in this way, so this is all you can look into that. So we take the ratio of gamma and gamma max, and then we multiply it with G, that is modulus of rigidity, and then we end up with torque, torsion, that is a tau max rho over C, and rho we know can vary from 0 to C. And we put this tau into the equation above of the torque here. So it will end up with rho max tau max rho over C into rho delta A. Tau max over C will come out, and the integral of delta square rho square dA, and this is called polar moment of inertia. We have discussed in detail while in the class. So so this torque will be equals to tau max over C, and this whole expression is called J naught. So that will be tau max J over C, and tau maximum shear stress will be TC over J. So T is basically the applied torque that will be calculated. C, or it will be given to you. C is basically the distance from the center. Obviously, C will be the maximum distance, and it will be rho if it is at any point other than C. And J naught is the polar moment of uh, inertia, or second moment of area. Another expression we came upon over here was phi TL over JG. So this was here. Tau max, basically tau max is now TC over J. Tau is tau at any other point other than C will be tau rho over J, and phi, the maximum strain, will be TLGJ, right? So directly proportional to the torque, more will be the twist, more length, more will be the twist, and more will be the angular deformation. Uh, more G, more rigid it will be, and more and lesser will be your deformation. Likewise, more moment of the area you have, larger area you have, definitely you will have more resistance to the deformation, so lesser deformation will be there. So inversely proportional to the modulus of rigidity, area, second moment of area, or the polar moment of inertia, and directly proportional to the T and L. These are all the parameters on which this phi exists. Then in the end, we did this example. If you remember, we had we have a beam on which different torques in different directions are being applied. This is the fixed point. So we did this, and we want to calculate the angular deformation of point A with respect to D, and we want to calculate tau. So simple, this is a statically determinate problem. T at AB will be minus 800 at this point. TB will be BC, section BC will be 800 minus 2400, so it will be 1600, and TCD at this section will be 800 minus plus 2400 plus 1000, so it will be 2600 pound inch. And then definitely we have we have to calculate phi A the deformation or the angular twist of point A with respect to this point D. So that will be the, obviously that will be the sum of all this, sum of all the deformation each particular section will be experienced. So it will be the, so net phi AD will be the sum of phi A, point A with respect to B, phi B with respect to C, and phi C with respect to D. One thing we did discussed over in the class as well, that we need to counter this direction once. Either you take it over here in the calculation of tau, or you take in the deformation when you are calculating the deformation. On both you cannot do this. So I would prefer that you take the direction. You don't consider direction while calculating the torque, but you need to calculate, but you need to consider this direction at the time of the calculating the angular deformation. So in this particular case, you will take minus and rest will be positive, and then you will keep on going. So first you will calculate the polar moment of area of J, that is pi by 2, 0.4 is the diameter. So that is basically not the diameter, sorry, that will be the radius. So it will be 0.4 raised to power 4. This is not the 2, this is basically the, it will be 4. So you will end up with this polynomial. Likewise for G base, J base, BC and J CD accordingly. And then you will calculate the tau AB, tau BC and tau DC. So tau CD, torques had already been calculated. C is basically the half of this diameter, that is obviously radius. And then you will divide it with the J, that is you have already calculated, and you will end up with this tau AB. And then at page 4 we discussed the stuff, what will be the phi. So now we are considering the negative direction over here. Rest all are done previously, that is all positive, but now you are considering the direction of that. So 800 will be in minus, this will be in plus, and this will be in plus, and this is basically TL by JG expression. You have already done that, and we end up with this 0.083 radians, and we calculated it in the degrees over here. So this was we have previously done during our class. Now there will be some changes in the there, so we will discuss one or two different scenarios that can come across in the while solving the problem. For example, now you have a pipe, or you have a beam. This is not a solid beam. This is basically a hollow beam, right? Initially, the dashed line shows that this is basically a pipe. This is not a solid tube. Then what will happen to you? Then what will happen? And this is the one case. So if we take the previous example, uh, this one. So what will happen if this tube, this is a solid tube, if I make it hollow, then what will be the difference of the solution? There will be no difference, except you need to calculate J accordingly. This is the formula J, this is the formula for the solid one. For the hollow one, it is pi by 2 into C, sorry, C inner 4, C outer 4 raised power 4 minus C, uh, that will be J equals to pi by 2 C outer 4 minus C inner 4. So this will be the calculation for the hollow pipe if you have this sort of, and if I draw this, so it will be the, this will be C1, and this will be C in, and this will be C out. This is how you can go. So this will be the difference between next one and this one. But what is now here? Now instead of having tube, I have an other material, that is the steel is inserted inside that tube. So now you have the total two materials. That is called composite material. So outer is a tube that is made from the brass, and inner side have a solid rod of the steel, right? So now it becomes statically indeterminate problem, because when you will twist it, the torque applied will be shared by these both brass and steel. This is the one body. This is the one rigid body, but made from the two different materials. But when torque will be applied on it, that torque will be shared equally by the by both steel as well as the brass. So if the torque is being bear by borne by both steel and the brass, so 600 newton if it is being applied on this side, so this torque will be equal to the T of brass plus T of steel, right? So now it becomes statically indeterminate, because we have two unknown: torque that is being applied on steel and torque being applied on the brass, that is equivalent to 600. So one equation, two unknown, so statically indeterminate. Then what we'll have to do? We'll have to go for this now twist, right? This is the one composite body. When you apply torque on it, it will twist. And when it will twist, that twist will be equal for both brass and steel. So phi of brass will be equal to phi of steel, right? So now we know phi. Phi is TL by JG, and this is for the brass. So T brass of the L of the tube, that is equivalent for both cases of for steel as well as brass, and G of brass and J of brass equals to T of steel over L G of steel and T of J of steel, right? Now what will happen? Torque of BR and the steel is unknown, length is known, G, that is the modulus of rigidity, that is the material property, that is known, G of steel is known, J of brass and J of steel again can be calculated. But how you will calculate? Brass is basically a tube, steel is basically a solid rod which have been inserted inside that tube. So for steel, you will calculate using pi by 2 into C4. That is the radius of that steel brass. But for the brass, you will use the formula of the hollow tube that I have written in the previous slide just right now. That will be pi by 2 into C outer 4 minus C inner 4. You can calculate that, and then you will put it. So T brass will be equivalent to the 0.729 T steel. Now T of brass comes in the form of T of steel. So now you will put this equation 2 in this equation 1, and you will calculate T of steel and T of brass. That will be 347 and 253. Net will be 600. Net of these will be 600. So what the difference is? So what is the meaning of this? All this is that this much 347 T torque will be borne by the steel, and 253 of that Newton meter torque will be borne by the brass. But since net is same, so the sum of this T steel and T brass will be equal to 600, right? So you will use this expression somewhere in the example, so it was necessary to discuss with you all this. Now another scenario is what we have been doing now, that one part is fixed till now what we are doing, one part is fixed, another part is free. That is generally used to call a cantilever beam. And the cantilever beam, not a cantilever beam, because we are not dealing with the beam, right? We are dealing with the rods of the circular cross sections. And second thing, what we are keep on doing till now, we are dealing with the uniform cross section. We are not introducing any sort of irregularity in the diameter. So we have a if we have a rod that is having same cross sectional area across the board, and same is case with over here. But that is the one end is fixed and the other end is free, and we are applying torque on one side of it. And when we apply torque on one side of it, it gets deformed and it gets twisted. Now, a situation may come in which you have both ends of that particular rod is fixed now. So what will happen then? So what will happen then, right? So okay, so if this is the case, so now there will be no movement at D and there will be no movement at B, right? But since two torques are being applied in the counterclockwise direction, that is 200 and 500 newton meters. So if I draw the free body diagram of this, so I remove these fixed beams, right, this A and D, and I'll draw a simple rod having 200 and 500 newton meters in a counterclockwise direction. Since these are in counterclockwise direction, so TA and TD will be opposite to that one, right? So if I if I write the static equation over here, that will be minus TA plus 200 plus 500 minus TD, that will be equal to 0, and net TA and TD will be TA plus TD will be equals to 700 Newton. Again, that is the statically indeterminate problem. Reason behind, we have two unknown, but we have one equation. So there are two systematic methodologies to solve this problem in this particular case. One is called superposition method, another one is called generic method. So we will not go into the details of the superposition method, but we will discuss with the generic method. So what is the generic method? Generic method is, since these two ends are fixed, so net phi will be 0 because these two will be 0. So A and D will not be moving because they are fixed. So net angular deformation of this A with respect to D will be 0. So total phi will be 0. So total phi is sum of phi A with respect to B, phi of B with respect to C, and phi of C with respect to D. So phi AB plus phi BC plus phi CD will be equals to 0. So this is the equation. Now we know what is the phi. Phi is TL over J and G. So how we will calculate the torque, right? So now let's see what we do with the torque. Now at this particular section, TA, what will be the torque? It is TA, right? But we don't know that what the TA is. In this BC section, what is? If TA is less than 200, so it will be 200 minus TA. And in this particular part, it will be 700 minus TA, 700 minus TA in this particular part. So when we will put this TA, 200 minus TA, 700 minus TA in instead of T in phi AB, phi BC, and phi CD, so we will have an equation in terms of TA that will be equal to something, right? And not something that will be equivalent to the in terms of the TD. So TA will have some value over there, and that TA will be put over here into in the form of TD over here, and then you will calculate TA and TD just we did in this previous example over here. And again, net deformation of both of these cases will be equal to 700. So you can go accordingly for this one. So this is all about a theoretical part, which we have already, most of the part have been already covered in the class, and the rest is being covered over here. So now we will come to the slides. So we will quickly go through these slides because all have been done, right? Phi is directly proportional to torque. I mean, the angle of twist, and the phi is directly proportional to length. This is what we have already done. So these are the final expressions in which T max is TC over J, and at any other point t tau is basically t rho over j. So this is example, that is example 3.01. Okay, I don't know. Okay, fine. Okay, fine. So example 3.0, example 3.0, we have a hollow rod, right? Torque is being applied into this direction. Inner dia is 40, outer dia is 60, and length is 1.4. So what we have to, what is the largest torque, T max, that can be applied to the shaft if the shearing stress is not exceed. So tau max is given, we need to calculate largest value of tau that can be calculated. So T is over here. So this is the formula we will go for. T is equal to T J tau max over C. And since it's a hollow rod, so we can calculate J. J is half into pi C2 over 4 outer radius and inner radius. So that is our J value, sorry. And now T is J tau max over C. Tau max is given to us 120 megapower, and C is basically 0.03 meter, and then 1.01 to 1 into 10 to the power minus 6 meter 4 is basically the J value of that particular one, right? So C is basically the distance from, that is the maximum distance. Obviously that will be half of this 60 millimeter, that will be 30 millimeter, and 30 millimeter is 0.03 meters. So we can calculate the maximum largest torque it can bear is 4.08 kilonewton per meter. And what will be the minimum shearing stress? Now we know minimum shearing stress where will be, it will be smaller the radius, smaller will be the shear stress. So it obviously it will be at the inner one as compared to the outer one. Because we know that maximum shear happens on the outermost surface of that one, and we know that outermost surface we usually called C, right? So now and we know that the torque will be increasing from inner radius to the outer radius. It will be minimum at the inner radius and it will be maximum at the outer radius. So obviously if T minimum and tau max, that is on the outer one and this is at the inner one, so this ratio of C1 over C2, or the ratio of inner radius and outer radius, should always be less than 1. So how it will be less than 1? It will be when you have inner radius divided by the outer radius. So inner radius is 0.02 and the outer radius is 0.03 into minutes, so it will be 80 megapascal. That will be obviously in the inner side of the or the inner diameter of the tube, or the shaft, whatever that is. Another problem 3.1. So shaft BC is hollow. This particular shaft is basically the hollow one. Rest this shaft and this shaft is basically the solid one. Shaft BC is hollow with inner and outer diameter of 90 millimeter and 120 millimeter respectively. Shaft AB and CD are solid of the diameter D. For the loading shown, these are the loadings. Torque A 60 kilonewton, 6 kilonewton, TB 14 kilonewton, TC 26 kilonewton, and TD is 6 kilonewton meter is applied on this shaft, and directions are already given. This is basically the counterclockwise, this is counterclockwise, this is clockwise, and this is again counterclockwise, right? So what we need to calculate? The minimum and maximum shearing stress in shaft BC, right? We have to calculate shearing stress in shaft BC, in this particular shaft, over here. right? So what we'll have to go, agar if we want to go for the A part of this, so we have to see what torque is being applied on this, and how we will calculate the torque being applied on this. Obviously this is 6 and this is 14, so it will be 20 over here if we draw the free body diagram, and in next slide we will go for it, and then we will solve it accordingly for them. The B part is required diameter of the shaft AB and CD if allowable shearing stress in these shaft is 60 megapascal. So here is the methodology. Cut section through the shaft AB and BC and perform static equilibrium analysis to find the torque loadings, and then apply elastic torsion formula for to find the minimum and maximum stress on BC, and then you calculate accordingly. So first is we cut the section AB, and sum of all the moments about x is equal to 0. So we know that 6 kilonewton is there. It is in the counterclockwise direction. TAB is in the clockwise direction. So it will be, one will be positive, another will be negative. So TAB will be 6 kilonewton kilonewton meter, and this will be it will be equal to the TCD. TCD means the last part of that, because they have the same torque and they have the same expression of diameters over there. And then the section is BC, so it is TBC is 20 kilonewton per meter. You can have an idea now how to calculate the TBC. And then since it is a hollow shaft, C1 is the inner radius, C2 is the outer radius, that is the 45 millimeter and 60 millimeter. So J will be pi by 2 into the hollow shaft formula, and we will come up with is 13.9 to 10 raised to power minus 6 M4. And tau max, we know where the tau max will be. Obviously tau max will be at C2, outermost radius. So tau 2 will be equals to TBC, that is being torque applied on this, that is 20, and C2 is the outermost radius, and J is over here. So we will come up with the 86.2 megapower. Now what we want to calculate, besides tau max, we want to calculate tau minimum as well. And tau minimum we know how to calculate. Tau minimum will be C1 over C2 multiplied by the tau max. C1 over C2, tau max will come over here. So tau minimum will be C1 C2 over tau max. Obviously ratio of the inner radius over the outer radius, so it will always be less than 1. So you will put over here and you will calculate tau minimum, that is 64.7 megapascal. And the third part will be given allowable shearing stress and applied torque, invert the elastic torsion formula to find the required diameter of the G, right? So now tau max is TC over J, T, because diameter is unknown now. For AB section, that is basically the solid rod. AB section is solid rod. ठीक है? So tau max is basically TC over J. TC and J we know for a solid rod is pi by 2 C raised to power 4, 65 megapower. That is the maximum allowable tau max given in the problem, and for that we want to calculate the diameter, that is twice the C value, and that is 77.8 millimeter. So if the tau max you don't want to exceed 65 megapascal, so this should be the diameter of this rod that can bear this much torsion, maximum torsion strength. Beyond that diameter will not be applicable, and then you will have to recalculate for any other value of megapascal shear stress, maximum shear stress one. Problem, sample problem 3.2. Again, you can look into that. That initial problem is a simple one, that you have inner radius, hollow shaft, inner radius, outer radius, and torque is being applied on that, and we have to calculate torque. We have to calculate for a given value of 12 ksi, that is the maximum shear strength that can be applied on that. So for the hollow shaft, J is calculated, tau max TC2 over J, because again C2 is the outermost radius and tau max will be maximum at the outermost radius, so we will go for the C2 value and then we will calculate it. Now what they are saying? They are saying that if we part B is if we replace by a solid shaft of the same weight, right? So what is the analogy now? This is the hollow rod, right? So what we need to do, to calculate the area of this, because area has directly relation with the length is same. So if we calculate the area, so volume will be same. When volume will be same, mass will be same, so weight will be same for all that one. So what we'll do, we will calculate this area, and we will equate that area to the equivalent area of the solid one. So what we did over here, so pi uh, outer radius minus inner radius, that is the area of the hollow rod, equals to pi c cube c3 raised power square. I mean, this is again for a solid rod having radius of c3, right? Pi r square. So c3, from here c3 comes 2.24 inch, means if we replace this hollow rod having inner and outer radius of 2 and 3 inch respectively with the one solid rod having radius of 2.24 inch, so that will have the same weight for that particular one. And if we have C3 now, so we can calculate tau max. Obviously C3 is the maximum radius of that, so TC3 over J maximum tau max is again 12 ksi, and we will calculate T211 kips per inch. So this will be the maximum torque that can be applied on that on that particular solid rod if we replace the tube with this one, with this solid one. Now, the third part is uh, if we replace, determine the maximum torque that can be transmitted by a hollow shaft of the same weight and of 8-inch outer diameter. So we need to calculate inner diameter. Again, now weight is same, right? And outer radius is given, inner radius is not given, but we have to calculate for the tube now, or the hollow shaft now, right? So again, area is same. We will calculate this. This is the known area that will be equivalent to the 4-inch given by this 8-inch outer diameter. So it will, C will be 4-inch, or the radius will be 4-inch minus C5, that is unknown to us. So C5 will be 3.317 inch. So if we replace this tube, the previous this one with this one, so what will happen then? How much torque that can bear? So by doing all this, so we will end up with the 636 kips inch. That is the amount of torque that can be transmitted by this particular shaft having outer radius of 4 and inner radius of 3.317 inch. So this is what we have already done, right? So phi angle of twist is TL over JG. This is we have discussed already. And as again, we have already discussed that our assumption till now was that we have a uniform rod having the same cross-section area across the board. Now what will happen if we have different cross-sectional areas like this one over here? You have TA over, you have A section A, section C, section point D, point E, and point B. Now you have two different cross-section area. A is a different than the EDC section, cross-sectional area, right? So what we will do in this particular case, as we have been doing into the previous chapter, that we include all the deformations. So here what we will do, we will calculate each angle of twist for each section, and then we will add up these all phi's, and we will end up with the net deflection of net change in the angle or the twist when a certain amount of torque is applied on one particular section, or the multiple torques being applied on multiple sections. So each section will be, phi of each section will be calculated according to their own areas and according to their own J's, and then you will add all these phi's, and you will end up with the net cumulative phi, or change of angle, or the angle of twist for that particular rod. This we have already done, that if we have one previously what we have been doing, that one is moving and other one is fixed, but in this particular case, if you see, both rods are fixed. It is all fixed, it is all fixed here. So this is what we have done, that statically TA plus TB will be 90 pound fit if that is being applied in the center. And the difference is that section A up to this point, it is basically a solid rod, and beyond that it is a hollow rod, right? So when 90 degree will be there, 90 pound foot torque will be inside. This is fixed and this is fixed, so net deflection will be 0. So phi of 1 plus phi 2 will be equal to 0, or you can say, as I did in my handwritten notes, that this phi will be equal to this one. Phi at this will be equal to this one. So that will be TA over L1 J1 G equals to TB L2 G2 J, and we can come up with the TB in terms of TA. And then we will calculate, since lengths are same, L1 is equal to L2 is 5 inch, this length is same. So we will calculate J1 for a solid, J2 for the hollow, and then we will come up with this T. And when we will put all these value into this expression, so we will come up TB in terms of TA, and this term will be put into this one, and then we will calculate TA and TB accordingly. So guys, we finish over here. This is the whole chapter is now completed except the gear one. So we will solve one problem of the gear and some basic theory of the gears in next lecture, and then we will finish this chapter accordingly. So I'll upload this whole lecture on the website, and the link will be shared with you on the Google Classroom, and then you can go through it. If you have any sort of query question, you can pose those questions to me through web, or you can email me, or you can pose the question in the Google Classroom as well. Once I have sufficient questions, so I'll have one complete I'll try to have one complete online session with you all guys, so the students who have the problems, they can come up with an interactive section with me. So I'll deal with this all queries accordingly. So time will be announced accordingly. So this will be our methodology. Hope I tried my level best. Obviously, there are some deficiencies that cannot be because we are not used to this methodologies, but we are trying to gauge you in this sort of activities, academic activities. So we will see how things move further, and accordingly we can have we can carry on our academic activities accordingly. So best of luck. Stay home. Stay safe. अल्लाह ताला खैर वाफिज रखे आपके तमाम जानने वालों के लिए, आपके अहलो याल के लिए, आपके बहनों भाइयों के लिए, आपके वालदैन के लिए। आगे आने वाले दिन ऑब्वियसली बड़े सख्त हैं, लेकिन अल्लाह ताला आपको सबको अपने हिफ्ज़ व अमान में रखे। अल्लाह ताला आपका हामी नासिर हो, और अल्लाह ताला आपको अब जहाँ जहाँ पे भी है एहतियात करें। ऑब्वियसली सिचुएशन इज़ नॉट एज गुड एज इट शुड बी। एहतियात करें, जितनी ज़्यादा अपने लिए करें, अपने अपने फैमिली के लिए करें, अपनी फैमिली को अवेयर करें कि दिस इज़ अ वेरी क्रिटिकल सिचुएशन। अल्लाह ताला हम सबको अपने हिफ्ज़ व अमान में रखे, खैरियत से रखे, अपनी पनाह में रखे, और हमें दोबारा से हमें अपनी वही एक्टिविटीज़ कंटिन्यू करने की तौफीक अता फरमाए, जैसे आज से हम 2 हफ्ते पहले, 3 हफ्ते पहले कंटिन्यू कर रहे थे। अल्लाह ताला खैर व आफियत रखे जनाब। बहुत शुक्रिया। अस्सलाम वालेकुम जी।